But alongside, by having this nice high-quality image in a 30 arc-second field of view around your primary target, it'll provide a great opportunity to build up a parallel deep survey over its duration and have spectroscopic information in those images as it's doing that. And I think lensing will be a valuable tool here, particularly because you're able to point at individual objects. You don't have to worry about the field of view. You can go for the best targets, and often they will be identified by lensing. And it'll have the power to see into the galaxy's internal structure. Now, why that's important, I think, is clear from the interstellar medium in our own galaxy and from nearby external galaxies, in that although we can find out a lot about the dynamics and the size and the stellar populations of galaxies if we look in the optical, if we want to know where the key action is taking place, then we look inside the molecular clouds. And even in the Milky Way, we can see 90% of the energy from this region in Orion is coming out in the far infrared. You do get a good idea of the dynamics looking at the optical. You see outflows, which you have trouble seeing in the far infrared. But if you actually want to know where the luminosity is coming from, and the astrophysics of why stars are forming in there and how they're forming, then we need to be able to probe the far infrared as well. So that requires it's crucial to get a multi-wavelength approach. We have to measure the spectral distribution of these regions across the full spectrum where all the energy is coming out. And although we don't really know a great deal about the detailed astrophysics of what's taking place in terms of the radiant transfer and the fine structure, we can get a very good idea about the total luminosity from the spectral distribution that comes through atmospheric windows, and which can be supplemented by space observations as well. On a galactic scale, and this just shows a visual representation of why it's again important to do this, running from the optical image, which contains a lot of spatial information, but is missing the most powerful source of emission from down here, which is visible at 15 microns, also in the IRAC bands in a composite from 3 to 5 microns, then at longer wavelengths still over the peak of the dust thermal emission at 350 microns. There's distinction between the morphology present at 15, 350 and 8 microns. So not just important to measure what's going on at the long wavelength, so just assuming the mid-infrared is a box, but it's also important to see from wavelength to wavelength what's happening. And if you redshift this kind of object, ALMA will be tremendously good at doing that, in combination with James Webb to provide a version of the optical and an extremely good version of the mid-infrared. And then to step again and say why it's important to do this at high redshifts. We know from the background radiation intensity that there is as much energy produced in the far infrared, shown by the proximate red curve, compared with the optical and UV, and so this process has remained important out to absolutely to redshift 1 and beyond. The biggest contribution being made recently is that Spitzer has been able to provide very high quality images at 24 microns, which allow about 20% of the background radiation to be resolved into individual sources. Those individual sources have a redshift distribution which extends to 0.7 at the peak and out beyond 1, and so it clearly shows strong evolution of population. At longer wavelengths still, and poorer resolution, ground-based images have resolved approximately 30 to 50% of the background, showing that out at higher redshifts again, there's still quite a lot of emission coming from far-infrared luminous objects. And we've got more information than just the backgrounds, but it's more difficult to compare the relative intensity if you look at the distribution of fluxes than if you just look at the background level directly. Now, an example of a region which shows the relative strength of emission at different wavelengths is this now 6-year-old image of the cluster Abell 1835, showing the optical members of the cluster and background galaxies, and then highlighting in contours the far infrared redshifted emission from background objects, magnified by a factor of order of 2 to 3, in this case from redshifts 2.5 and 2.3 for the most powerful sources of emission. And it shows that our current capabilities allow us only to see a very small fraction of the total galaxies present in the far infrared. Now, the energy coming from these galaxies is comparable to of the energy from all the optical galaxies in the background of the cluster, but only 2 are very significantly detected. ALMA will revolutionize this and give us a picture in the far infrared, redshifted to the submillimeter, which matches the optical resolution. There's about 25 images of clusters like this. Many of them have got redshifts, and by adding Spitzer information as well, we get a better idea of the spectral energy distribution of these galaxies and find new examples. The problem we have, though, so far is almost every example of a galaxy with a good SED and a multi-wavelength study are all in the ultra-luminous class. They don't connect with the well-established luminosity function of galaxies from Lyman break surveys and from redshift surveys. They're just separated in flux too much. If we want to go inside galaxies to get information about the astrophysics at the moment, we can do that in an unresolved way. We can get a spectrum of CO rotation lines. I'm showing what the molecular gas is doing in ultraluminous galaxies, admittedly. This paper by Kartik-Sheth et al. Shows a multiple image in Abel 2218, detected in the continuum in the submillimeter shown by the contours, and then with an image from the OVRO interferometer overlay showing individual detections of line emission associated with CO at each of the centers of the 3 multiple images, and then it is overlaid on the HST image. This provides us with an estimate of the mass of these objects, estimate of the mass of the molecular gas inside, which is typically comparable to the stellar mass you estimate from the optical colors, and is associated with objects of 10 to the 11 solar masses, also within a few kiloparsecs. So they're not only luminous objects, they're also massive objects. So we're looking at the top end of the mass function and the luminosity function happening at moderate redshifts, here at 2.5. In some cases you can get higher quality spectra. This shows a small galaxy in another cluster field, which is magnified to give a very high quality spectrum from the Plateau-de-Bury interferometer. And another example of a galaxy not lensed, no, it is lensed this time, yeah, Abel 851 good source, which is actually, although a single object in the discovery images at sub-millimeter wavelengths, is split into 2, each of which has an individual detection at higher resolution from the ERAM interferometer and a very clearly defined velocity width, hopefully giving some idea about the dynamical mass of that system. This is also possible to extend to the infrared. As yet, I don't have any information about the nature of these things in an IFU spectrum, but from a long slit spectrograph, you can certainly see velocity structure inside these galaxies. This shows a NIRSpec 2-dimensional spectrum of both H alpha and nitrogen-2, with some extension and some shear in the line running through the middle of this galaxy in the HDF. We've got about 25 of these spectra, and according to whether the optical lines in these galaxies are identified with AGN emission or not, then you can see a relatively strong or weak underlying broad line component in an infrared spectrum, in principle telling us a bit more information about the power source and whether there's an AGN present and how much it controls the luminosity of these objects. We've been trying to get some metallicity estimates from oxygen line ratios, which is coming along but is time consuming, and hopefully is something which will become much more